Okay, our next topic is zeros of polynomial functions. We did this earlier on, but now we're going to look at more complex, not from a mathematical, but just from a difficulty standpoint. Even though some of the zeros could be complex. Now, one thing to point out is a lot of times in this class, the zeros are integers or rational numbers, but a lot of times they're not. So don't think all solutions will be like these. Okay, so the fundamental theorem of algebra says this: if a function f of x is a polynomial of degree n, where n is greater than 0, so if n is 0, then you just have a horizontal line. So it's got to be a line or a parabola or a cubic or something like that. Then f has at least one 0 in the complex number system. So for a linear expression, you have one x-intercept. That's what the zeros are. For a second order polynomial, you can have two real, well, I guess you could have 1, 2, or 0, 0, 1, or 2. If you have 1, it's a repeating root. If there's 2, then it's not a repeating root. If it's none, it means you have two complex roots. If you have a third order polynomial, you can have 1 real and 2 complex, or 2 imaginary, or you can have 3 real. Because you always, with complex roots, you always have to have two of them. They always come in pairs. Whereas for an odd degree polynomial, you're always going to have an odd number of real zeros. Okay. Then we have this linear factorization theorem. It says if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors. And the linear factors can be either, well, it says here complex. So let's just kind of expand on that. Let's say you have x minus 6. That's a factor. Is negative 6 a complex number? The answer is yes. Okay. Why can I say that? Because I have negative 6 plus 0 I. So any real number is a complex number. Now you also have complex numbers. I might have x plus 4 minus 3i. So this 4 minus 3i is obviously a complex number made up of a real part and an imaginary part. So that's a complex number. Now, if you had something like x plus 7i as a factor, then 7i, that is also a complex number because you have 0 plus 7i. So just because it's missing either the complex part or the real part, it still makes it a complex number. Okay, so if we have a third order polynomial, we're going to have 3 roots. As I said just a minute ago, you can have 1 real and 2 complex, or you can have 3 complex. If you have 4, say a fourth order polynomial, then you can have 0. You can have 4 complex, 2 complex, and 2 real, or all real. You couldn't have 1 complex because those always come in pairs. Okay, so now how do we determine the zeros? Well, what you basically do is you you start with your polynomial, and then you guess at what the zeros might be. And then you can use synthetic division or long division and see if that guess gives you a zero remainder. If you get a zero remainder, then it is a factor or a zero. Now, so there, you can have two kinds of zeros. You can have rational zeros, or you can have irrational zeros. Is any one more likely than the other? Probably not. But for rational zeros, there are a certain possibilities. There's not an infinite number of possibilities. There's a finite number of possibilities. And it depends upon the coefficient in front of the highest order term and the coefficient in front of the constant term at the end. So here is what it says. Well, first, what is a rational number? Well, a rational number is just the ratio of two integers. So an integer can be a rational number. 3 is 3 divided by 1, 3 over 1. So 3 is an integer, 1 is an integer. So 3 is a rational number. Or they could be, the denominator could be something other than 1. So you might have 3 halves, 3 over 2. So again, the numerator is 3, the denominator is 2. They're both integers. Therefore, that's a rational number. So what this test says, if the polynomial f of x is equal to some constant a sub n times x to the n power plus some constant a sub n minus 1 times x to the n minus 1, so on forth, all down till a sub 2 x to the second power plus a sub 1 x to the first power plus a sub 0 times x to the 0 power, and the coefficients are integers, then every rational zero, if they exist, of the function has to be of the form p divided by q, and p are the factors of a sub n, and q are the factors of did I get that right? P is the factors of a sub 0, which is the constant on the end, and q are the factors of the leading coefficient. So I got those mixed up. And that's if P and Q have no common factors in the 1. What you can do there is you could divide. If a sub n and a sub 0 have a common factor, then you would divide the whole expression by whatever that common factor is. So we'll see what that means in a second. Okay, so here's a third order polynomial. So what we could say is a sub 3 equals so a3 is negative 3, a2 is 20, a sub 1 is negative 36, and a0 is 16. So in this case, p is equal to negative 3. I did that wrong again. That's q. Q is equal to negative 3, and p is equal to 16. Okay. Now, what we do then is we look at the factors. So factors of negative 3. So, and actually it's plus or minus the factors. So, the factors, let's just say the factors of 3 are 1 and 3. Those are the only two whole numbers that we can multiply. So we actually can use plus or minus 1 or plus or minus 3. It's always plus or minus these numbers. And then you can do the same thing, the factors of 16. So that's going to be 1 and 16, 2 and 8, and 4 and 4. So those are the factors. So we can use plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and plus or minus 16. Okay, now, so what we're going to look at is P over Q. So in reality, that's actually wrong here. It's been a while since I've taught this thing. So P and Q are these factors. So this is P. So this is Q, and this is P. So what we can do is we can have all of these be the numerators. So we'd have plus 16, plus 8, plus 4, plus 2, plus 1, and with that you can either have 1 as the denominator, or those same numbers in the numerator, but the denominator being 3. Now, what happens with this, the plus or minus, is if I have both pluses, then the answer is plus. If I had both minuses, it's minus. So ultimately what happens is you just take the ratio of these numbers, 16 over 1, 8 over 1, and you can have plus or minus. So you always get either plus or minus. If I choose one to be positive, the other one to be negative, then the result's going to be negative. If I choose both of them to be plus, the answer's going to be plus. If they're both negative, they're going to be plus as well. So all I have to really do is then put plus or minus in front of all these. And if I get any repeats, then I can eliminate those. So it can be plus or minus 16. So again, one last thing I can do is I can simplify these. So this is 16 plus or minus 16, plus or minus 8, plus or minus 4, plus or minus 2, plus or minus 1. And all of these you can't simplify. So plus or minus, it's going to be plus or minus 16 thirds, plus or minus 8 thirds, plus or minus 4 thirds, plus or minus 2 thirds, plus or minus 1 third. And all those, so how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 one sign and 10 the other sign. So there are 20 possible rational zeros. Okay, now how do you determine if any of those are roots or zeros? Well, what we can do is we can take the original equation and if we divide this out, so let's say guess, again this is a guess, x equals 1, that's this plus 1, which is the same as the factor x minus 1. So if I move this to the other side, it becomes x minus 1. So the question is, if I take negative 3x cubed, negative 3x cubed plus 20x squared minus 36x plus 16, and I divide by x minus 1, and if I get a polynomial with a remainder of 0, then this is a factor, this is a 0. Now the easiest way to do this problem is to use synthetic division. So what I would do is I'd write out the coefficients of the original polynomial. And the number I put here is not the factor, but it's the 0. So I'll bring negative 3 down. 1 times negative 3 is negative 3. 17 plus negative 3 is 17. 20 plus negative 3 is 17. 1 times 17 is 17. Negative 36 plus 17 is going to be negative 19. That's right. Yep. 1 times negative 19 is negative 19. I add these together, I get negative 3. Okay. So the remainder is not 0. So I can say, therefore, x equals 1 is not a 0. X minus 1 is not a factor. One other thing I can do is I can say f of 1 is equal to negative 3. So whatever I use here, and the remainder is always the value of the function. So it's pretty close to 0. It's not equal to 0. So you might think, I wonder what, well, f of 0 is always easy to figure out. So let's plug f of 0 in there. So if you put 0 in here, you get 16. So I don't, so it's somewhere between 1 and 0. There is a root between 1 and 0. Which numbers here are between 1 and 0? Well, 2/3. So that's a possible, that would be another possible value. Let's just see. I don't think it actually is just based on those numbers, but we can try it out. So, if I guess that the 0 is 2/3, or the factor is x minus 2/3, what I would do is I'd take the original polynomial again, negative 3, 20, negative 36, 16. Here I'd put 2/3. Okay, so negative 3, bring that down. 2/3 times negative 3 would be negative 2. 20 plus negative 2 would be 18. 18 times 2/3, well, 2 times 18 is 36. 36 divided by 3 is 12. So this is going to be 12. Negative 36 plus 12 is negative 24. Actually, I think it is going to work out right. 2/3 times negative 24. So 2 times 24 is 48. 48 divided by 3 is 16 times the negative sign. It's negative 16. You get 0. Ta-da! So what that says is that, therefore, x equals 2/3 is a 0, and x minus 2/3 is a factor. So that's pretty cool. Now what I have left over is negative 3x squared plus 18x minus 24, which is, if I factor out a negative 3, that'll be x squared minus 6x plus 8. And now I can possibly do this by observation, which I can. So I'm going to have x here and x there. Well, two numbers multiplied together to get 8, added together gives 6. Well, the answer is 4 and 2, and they're both negative. Negative 4 times negative 2 is positive 8, and then negative 4 plus negative 2 is negative 6. So what that ultimately means is that the original expression, which was negative 3x cubed plus 20x squared minus 36x plus 16, that is equal to x minus 2/3, the whole thing times negative 3 first, so that comes out. Then I've got this factor, and I've got x minus 4 and x minus 2. And so that is, this third order polynomial can be factored. And there are 3 factors, and there are also 3 zeros. So the zeros would be x equals 2/3. So you set that equal to 0, solve for x. The second one would be x equals 4, and x equals 2. So those are zeros. They're also the x-intercepts. Those are the factors. And we can actually check this out. So let's open up the graphing program here. So what I'm going to do is I'm going to plot this original function, which is negative 3x cubed plus 20x squared minus 36x plus 16. Now, because this is a negative leading coefficient, it's going to start up here and it's going to come down and wiggle a bit, and it's going to end up down that way. So you can see there, I've got three x-intercepts. If I zoom out in the y direction, I get that. Notice the y-intercept is 16 because that term there is 16. We've got one intercept here at x equals 2/3. X-intercept at, it says 2. I said it was, oh yeah, we've got 2 and 4. I just didn't see, there's the 4, there's the 2. So you can see it worked out. 3 just does some stretching. So that's kind of how it works. So let's kind of review what we did here. You take the original function. P are the factors of the constant term. Q are the factors of the coefficient in front of the highest order term. And they can be either plus or minus. Ultimately, what you do is you take the ratio of each one of these terms, the P terms to the Q terms, and say they can be either plus or minus the result. So taking these 5 numbers, dividing by 1, and then putting plus or minus in front of them, and simplifying, give me the factors. These are the P divided by Q terms. Likewise, you can do the same thing. You take each one of these 5 numbers, divide by the other 3, so you get plus or minus each one of those. So 20 possible rational zeros. And you can also, the one that I chose was 1 originally, which didn't work. But I was able to see that when x equals 1, that y is equal to negative 3, which is pretty close to 0. So I said, oh, there must be, maybe there's a rational 0 near there. And so I said, well, let's evaluate it at 0, because that's easy. F of 0 is 16. So I knew that the intercept had to be somewhere between x equals 1 and x equals 0. And I looked over here and said, oh, there's only one number that's between 1 and 0 that's positive. So I tried that. I did use synthetic division, came up with the 0 remainder, so that meant that it was true. And then I could use the coefficients down here to rewrite what was left over. I factored out a constant. I factored it by observation. And you'll notice that the other 2 zeros, 2 and 4, are in my original list here of possible rational zeros, 2, 4. So all of them showed up there. It's just the last 2 I didn't need to go back here and I just could factor it. So, some of this requires guessing, some of it requires a little bit of thought in terms of if you get the remainder to be close to 0, then you might be close to the right answer. Once you guess one of the factors with a third order polynomial, you should be able to get the other 2 factors, because the polynomial division will give you the remaining quadratic equation, which we can solve either using quadratic equation, completing the square, observation, whichever one's the easiest. Now, if you have any complex solutions, they're always complex conjugates. Now, why is that? Well, because the product of the two complex roots have to be a real answer, because the original polynomial was only made up of real parts. So when you factor it, you end up with a complex factor. The other complex factor has to be the complex conjugate. So when you multiply those two complex numbers together, you get a real number. Okay, so that's why they occur in pairs. We'll see that in a second. Okay, what does this say? Factors of polynomial. For every polynomial of degree greater than 0 with real coefficients can be written as the product of linear and quadratic factors with real coefficients. So if you're limiting yourself to real factors, then you're going to end up with linear or quadratic factors. The linear ones are going to be real. The quadratic factors, if you can factor those into reals, then you've got all real results. But sometimes a quadratic factor cannot give you a real result. You might have a complex one. Okay. So I'm trying to remember what that meant. Oh, I know what it is. So if you take this green curve, which is a third order polynomial, and you factor out the linear part, you'll have a linear part which is a real 0, and then you have this quadratic which has no x-intercepts, and therefore it has no real zeros. So the original third order polynomial here, which also only has one x-intercept, which is due to the linear part. But if I were to have something like this, so my original third order polynomial has 3 x-intercepts, therefore 3 real zeros. If I factored it initially, I'd find out one of the factors is this value. And this blue line would represent the linear factor. The quadratic factor would also have 2 real zeros, which would end up being the other 2 real zeros of the initial third order polynomial. You can also have, what you could do is then take this red curve and factor that, the quadratic term, and factor it to end up with 3 linear terms. And each linear term can be shown as a line. And each intercept for each line is one of the zeros for the third order polynomial. And to get this number, you take this times that times that. You take the value of the linear equations, add a particular value of x, multiply those together. That'll give you the resulting third order polynomial. So that's why when this green curve is 0, the yellow curve is 0. These two are non-zero, but if you take two non-zero numbers and multiply by 0, you get a 0 result. Same thing here. The red curve is 0. The blue curve is not 0. The green curve is not 0, but multiplying these three together gives you 0 because one of them is 0. And finally, this last intercept, the blue curve is 0. The red curve is non-zero. The green curve is non-zero, but non-zero times non-zero times 0 always gives you 0. So it's just an interesting way of thinking about factoring things, not just as factors, but as those factors as linear equations. Okay, so the first one we were given third order polynomial, and we had to figure out what the factors were by just guessing using the rational zero test. Sometimes we are given one of the complex zeros and we're asked to find the other two. So that's pretty easy. So what we're saying is that one of the zeros is 5i. There's just an imaginary part. There's no real part. So this is the same as 0 plus 5i. So the complex conjugate of that would be 0 minus 5i. And that wouldn't be 5i minus a 0 because it's the same thing. So it doesn't really help any. Now why is that? Why do I know this is another root? Because they always come in pairs. Complex solutions always come in pairs and they're complex conjugates of each other. So I know that this initial polynomial is made up of three factors. One is going to be x minus 5i, which is associated with this 0. And I'm going to have x plus 5i, which is associated with this one. So if I drop that and move that to the other side, I'll get x plus 5i. And then there's a third polynomial over here, which I don't know at this point, but I will be able to figure it out here just shortly. So what I'll do is I'm going to multiply these two parts together, the two complex parts together. So I use FOIL, so I get x squared. Because it's a complex conjugate, the imaginary parts fall out. So I get 0x. And then I have negative 5 times 5, which is negative 25, times I squared, which is negative 1. So that becomes 25. So these two terms, when you multiply them out, become x squared plus 25. So to find this third answer, what I do is I'm going to use long division. So if I take, so what we have here is the product of these two factors, and we get this quadratic term x squared plus 25. So to find the third factor, which is the real factor here, or the real zero, is we need to divide the original polynomial by the quadratic term. And we could do that two ways. We can use synthetic division, or we can use long division. And the reason those things were already up were because I made a mistake, and I was trying to figure out what mistake I made. So I've figured it out, which is, took me a long time to figure it out. It wasn't that hard to figure it out. So anyway, the question is here, what do I need to multiply by x squared by to get 2x cubed? The answer is 2x. So 2x times x squared is 2x cubed. 2x times 25 is 50x. That was the problem. I put down 50x squared because I forgot that there's no linear term in there. Okay, then you subtract these. So this goes to 0, that goes to 0. You're left with 3x squared plus 75. So now the question is, what do I multiply x squared by to get 3x squared? Well, the answer is 3. 3 times x squared is 3x squared. 3 times 25 is 75. Subtract those, I get 0. So my additional factor here is 2x plus 3. So the 0, the real 0 is, you set this equal to 0. So you set the factor equal to 0. And if you solve for that, you'll get x is negative 3/2. Now, I can do the same thing over here. Actually, this is to confirm that this is the 0. So if I put 3/2, if I take the original polynomial and divide by x, so the factor is actually x plus 3/2 equals 0. What'll happen is you bring this down 2 times negative 3 halves is negative 3. 3 plus negative 3 is 0. Negative 3 halves times 0 is 0. 50 plus 0 is 50. 50 times negative 3 halves is negative 75. So if you did that, you get what you would get is 2x squared plus 50, which is the same as 2 times x squared plus 25. So anyway, that was kind of to check. What I did is I plotted this function, found the 0 was here, and I just wanted to see why I couldn't seem to figure it out. It was one of those cases, just had a mental problem. Okay, so the same kind of deal here. So this says that one of the zeros is x is equal to 3i. So the corresponding factor associated with x equals 3i is x minus 3i is the factor. So the complex conjugate would be x plus 3i. So that's the other 0. The other complex 0 is the complex conjugate. So if we now multiply these things together, we'll get x squared. The inner and outer will cancel out. You'll have negative 3 times positive 3, which is negative 9. I times I, which is I squared, which is negative 1. So we'll get x squared plus 9. So that is the quadratic term that has no real zeros, but it does have 2 imaginary zeros. So again, what we can do to find that last factor that we're looking for, the last 0, is we're going to take the original function. We're going to divide by this quadratic term. Okay, what do I need to multiply x squared by to get x cubed? X. X times x squared equals x cubed. X times 9 is 9x. I subtract both of those terms from the original polynomial. So this goes to 0, this goes to 0. I'm left with x squared plus 9. What do I need to multiply x squared by to get x squared? The answer is 1. 1 times x squared equals x squared. 1 times 9 is 9. Subtract that, you get a remainder of 0. So the original function can be shown as x plus 1 times x minus 3i times x plus 3i. So the third 0 is x equals negative 1. You're saying, well, it's positive 1 over here, but no, that's, we set the factor equal to 0. Solve for that. That gives us, setting the factor equal to 0 gives us the 0. So it has one real 0 again, 2 complex zeros. Okay. So let's look at this one. So it's missing the x squared term. We're not given any information, so we're going to have to guess what they are. So what we're going to do is we're going to look at the use the rational zero test. So the factors of 6 are plus minus 6, plus minus 3, plus minus 2, plus minus 1, q, just plus minus 1. So if we look at p divided by q, it's basically all these numbers. Plus minus 1, plus minus 2, plus minus 3, plus minus 6. So these are the zeros, possible zeros. So what we can use synthetic division to do this the quickest way. Put the coefficients of the original polynomial in. Remember, there's a 0 for x squared. And typically, you choose 1 first. See where we get. So we're going to choose 1. X equals 1. So we bring 1 down. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 1 times 1 is 1. Add this together is 0. 1 times 0 is 0. We get 6. Okay, so what that says is, in this case, the function's h, not f. So we get h of 1 equals 6, which is pretty close to 0. So we might want to try 2 next. So let's try x equals 2. See what happens. 2, 1, 0, minus 1, 6. So we bring 1 down. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. Negative 1 plus 4 is 3. 2 times 3 is 6. 12. Okay, so it's going in the opposite direction. Make sure I did all that right. Bring that down. This multiplied by that. Add those together. Multiply that by that. That's good. Okay. So that means I should probably try negative 1. So negative 1, 1, 0, negative 1, 6. Bring that down. Negative 1 times 1 is negative 1. 0 plus negative 1 is negative 1. So then we have negative 1 times negative is 1. 0. 0 times negative 1 is 0. 6. Interesting. So it says that x equals, and so again, h of 2 is 12, and h of negative 1 is 6. Does that make sense? Something doesn't make sense. Because if you do x of 0, you get 6. So how the heck is that happening? Because if h of 1 is 6, h of negative 1 is 6, and h of 0 is 6. That's some strange behavior. So let me just double check my numbers here. 1 times 1, 0, 1, 0. Okay, makes sense. Negative 1. What does negative 1? Negative 1 times 1 is, yeah. Well, that seemed to work. Okay, let me just double check this one, see whether that. Okay. So that seems to be right. So I'm still puzzled. So I'm just going to think about this for a minute. So let's just plot these points. So here's negative 1, here's 0, here's 1, 2. So it says h of 0 is 6. It says h of negative of 1 is 6. H of negative 1 is 6. And this one's like that. So I don't know how that happens, because you think it goes like this, if it goes back up like that, it would have to go back down like that. So I guess that's possible. Okay, well, that's the only thing that can happen. So that just kind of blew my mind. So the other option now, because of that, and this is positive, so it has to go, the end behavior says it has to happen this way. So it looks like negative 2 might be a good choice. Let's see what happens there. Negative 2, 1, 0, negative 1, 6. Okay, so you bring 2 down. Bring 1 down. Negative 2 times 1 is negative 2. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is positive 4. Negative 2 times 3 is negative 6. 0. There we go. Okay, so what that's saying is that x equals negative 2 is 0. Now this would indicate that there are no other real zeros, and you can figure that out because you can take what's left over and make the quadratic out of that. Okay, so that is what's left over. Now, if we wanted to factor that, we could use completing the square. So we take, move this 3 over there, and what we're trying to do is find out what values of x make that go to 0. So we take the coefficient in front of x, divide by 2, square it, which is negative 1 squared, which is 1. So we add 1 here, and we subtract 1 there. So that becomes x minus 1 quantity squared, and that's all equal to 0 up here, plus 2 equals 0. So we would get x minus 1 squared equals negative 2. Take the square root, we get x minus 1 equals plus minus the square root of negative 2. Square root of negative 2 is going to be square root of 2i, so it's going to be plus or minus the square root of 2 times I. Square root of negative 1 is I. And then we add 1 to both sides, so we get x is equal to 1 plus or minus the square root of 2i. So now we have all 3 zeros. 1 0 is, here are the zeros. So it's x equals negative 2, x equals 1 plus the square root of 2i, and the third one is x equals 1 minus the square root of 2i. So again, once you find one real zero, then you can either get the other 2 real zeros by factoring whatever you have left over. In this case, the thing we had left over was not didn't have any real roots. It had complex roots, but it still gave us 3 roots. And also this, when you try dividing using synthetic division and you end up with a remainder, you can use those to kind of think what's going to happen. So I had the points 2, 12, 1, 6, 0, 6 from the y-intercept, and negative 1, 6. And then I thought, oh, well, how can that actually happen? Well, the only way that could happen is if this thing looped down and looped back up again. And that led me to believe that this would not loop down far enough to go through 0. So I said, oh, there's probably only 1 0, and it's got to be less than negative 2. It's got to be pretty close to negative. It's got to be less than negative 1, because the way this thing was moving, it looked like it had to, this one here is 6 greater, so this one's probably 6 less. So that's something that kind of comes with experience. Okay, so that was it. Before we finish there, let's look at how you would just to prove that what we had here is the truth. So what I'm going to do is I'm going to take this. So the original equation can be factored. The factors look like this. Those are the zeros, but the factors are going to be x plus 2 times x, and then we'll have minus the zeros. So you have 1 plus the square root of 2i. So that's one factor. I need one more parenthesis here. It's not quite right. So there we go. And then the third factor is going to be 1 minus the square root of 2i. Okay, so that's the original function. What I wanted to talk about was, what do you do here? So the best thing to do actually is to leave them in the parentheses. So you have the whole second term. You treat this as one term, not as three terms. You'll see why in a second. Okay. Okay, so we're going to use FOIL. So first you'll get x times x, which is x squared. Then you'll have, so that's f. O is next, outer. So you get x times that, which is going to be negative the quantity 1 minus the square root of 2i. Then you have the inner, which is these two. So again, I'm going to switch the order. You'll have a negative sign from here. So what we're doing is taking x times that. So we get plus x times negative 1 plus the square root of 2i. Okay, so x times this. Here we take x times that. And then you have negative times the negative. So that'll be positive. So this times that's positive. And then you have 1 plus the square root of 2i times 1 minus the square root of 2i. So those are the three terms. Now, when you multiply this out, you'll have x times negative times 1. So for this part, you get negative 1 times x. So that's negative x. Now the second part, you have x times negative times this part. So that's going to be plus, because you're going to have this minus times that minus. And then you have x times the square root of 2i. So it's going to be x times the square root of 2i. This times that, sine times that, times the whole thing. Okay, now we go to the second one. You have x times negative 1. So that's negative x again. Then, where are we in this thing? Okay, then we have the last part. So you have x times, no, this one here, you have x times negative times positive square root of 2i. So this ended up being positive x square root of 2i. This becomes negative x square root of 2i from this times that times that. And then the last part, you've got 1 times 1, which is 1. You've got plus square root of 2i times 1 and minus square root of 2i times. So the inner part of that multiplication goes to 0. And then the last part is you have the square root of 2, and we got a negative sign here. So it's negative because positive times negative is negative. Square root of 2 times square root of 2, and then I times I squared. Okay, you see those cancel out. This is plus x squared root of 2i. This is minus x squared root of 2i. These two combine into negative 2x. And then finally we have plus 1. This is 0. Drop that. You end up with negative 2. Square root of 2 times square root of 2 is 2 times I squared, which is negative 1. So what we end up with is x squared minus 2x plus 2, which I think is what we had, right? Trying to remember if that's what we had here. No, actually we didn't. That's not right. This is actually 3. Okay, so this becomes 2. 2 plus 1 is 3. Okay, that makes sense. So that matches up x squared minus 2x plus 3. So when we were down here, that was what we had left over when we correctly guessed the single real zero. We ended up with this as the quadratic expression, which we ultimately factored or solved for using completing the square. So anyway, I just wanted to show you how you would go backwards from the factored result, and how you deal with multiplying two factors together, where one of the second part of the factor is a complex number instead of just a real number.